Hi, I'm Bora and this is our Physics 211 project. The aim of this project is to calculate the reaction rate constant in sucrose inversion in an acidic solution. So here we have our setup. We have a glass container which is a tube shaped, and we have two polarizers with an angle difference of 45 degrees, as you can see. And we have a telecentric lens and a convex lens, and we have our point light source. So the fundamental phenomenon we use in this experiment is the optical activity of chiral molecules. Chirality, or chiral molecules, is the molecules which cannot be superimposed on their mirror image by translation or rotation. So if I take my right hand to be a chiral molecule and move it like this, or rotate it like that, I cannot reach my left hand, which makes either of my hands chiral. So it turns out that chiral molecules change the rotational plane of polarization of light when light passes through them. And sucrose, with its monosaccharides, glucose and fructose, are chiral, and they each rotate the polarization plane uniquely at a different angle. So during sucrose inversion, as the concentrations change, we can get a brightness difference by using two polarizers at two ends of the sucrose inversion, where sucrose inversion takes place, and get a gradual difference in brightness, since the maybe, let's just say, the initial polarization of light as it comes out of the solution is like this, and at the end, when sucrose inversion is completed, it becomes this. So it may move like this, or do a 2 half turns, or and half turns, let's just say. We get a brightness difference at the end, and this enables us to determine a reaction rate constant at the specific temperature and specific pH. Next is the video how things would happen in a system with hydrochloric acid and sucrose solution mixed. So as light comes out here, we have a telecentric lens whose focal length is 1 meter, and with this telecentric lens we collimate the beam, and going through this solution, the polarization of light changes, the plane of polarization. So and we heat this tube with a blowtorch, and keep it at the same temperature, so the reaction changes in a constant rate. So as the reaction occurs and goes on, we have different glucose and sucrose concentrations and sucrose concentration. So that results in a difference in the total change of polarization plane of light. So we have two polarizers here. We have, as I said, a convex lens here, and then what we do is to focus this light on a camera, and then we take the data on that camera, we take the brightness of that data, then we, depending on the data and the brightness change, we calculate the constant of reaction rate. So by using the OpenCV library of Python, we can calculate the average brightness in each frame of a video, and then calculate the average difference between the frames. By using the difference and average brightness data and correlating them with the optical rotation, we get this plot, whose on the y-axis we have the optical rotation, and on the x-axis we have the time. But this plot is a logarithmic plot, because as the sucrose inversion occurs and continues, the concentrations change in an exponential manner. Then we just take the natural logarithm of the data we have and acquire this plot. Using this plot, we acquire a reaction rate constant of this, and with the with pH equal to -0.6 and temperature at 52 degrees Celsius constant. Then by using this, we can also acquire a activation energy for acidic sucrose of acidic sucrose inversion at the specified temperature. So, and we get this activation energy. So we have a percentage error of 0.6 on the reaction rate constant. So this percentage error implies that it is quite convenient to use a polarization-based method of measuring reaction rate constant when dealing with reactions which consists of chiral molecules or chiral elements. Thank you for watching.